Okay, so we're going to start with 9.1, which covers algebra and composition of functions. This lecture will correspond with homework 21A. Number 1 gives us two functions, f of x and g of x. And for the instructions, what we're going to do is the algebra of functions. We're going to do addition, subtraction, multiplication, and division. So first, addition looks like this. In part A, or the first question, f plus g of x. Okay, that's pronounced f plus g of x. And what is f plus g of x? F plus g of x is just the same thing as f of x plus g of x. These are notationally the same thing. Two different notations to mean the same thing. So in order to simplify, all you have to do is replace f of x with what f of x is equal to, and replace g of x with what g of x is equal to. Okay? So f of x is x squared plus 8x plus 7, and g of x is x plus 1. And then we add these together. X squared, 8x plus x is 9x, and 7 plus 1 is 8. So that is f plus g of x. Now this kind of question is going to be 4 parts. We're going to do f plus g of x, f minus g of x, f times g of x, and f divided by g of x. Addition, subtraction, multiplication, and division. And so you have homework questions related to this, and there's also one question on the final exam that covers this. It's worth 1% of the final exam. It's one of your short answer questions. And it will ask you for all 4: addition, subtraction, multiplication, division. So that's addition. So now the next question is, how do we do subtraction? What is f minus g of x? So f minus g of x, let's turn this plus into a minus. F minus g of x simply means f of x minus g of x. So where I did have a plus sign between the two functions, now I have a minus sign. Now before, when I had these parentheses in place, those parentheses were just there to show you that I was replacing f of x with f of x and g of x with g of x, and they didn't mean anything with addition. With subtraction, this second parentheses means something, right? Because the subtraction sign is going to have to distribute across. So let's erase this part. When we have subtraction, x squared is still x squared. Then we have 8x minus x, so that is 7x, and 7 minus 1 is 6. So that is subtraction. So addition and subtraction, really simple. Next comes multiplication. So f times g of x is the same thing as f of x times g of x, which is the same thing as your two functions being multiplied together. Now, of course, you don't have to have this dot here for multiplication. You can just have the two parentheses side by side. And when you have those two parentheses side by side, then you have multiplication. And this is a trinomial being multiplied by a binomial. You can do horizontal long distributive property, or you can multiply this vertically. But in the end, after you multiply these, you should end up with, since x squared times x is x cubed, you have x cubed. Then you have an 8x squared and a 1x squared, so that is 9x squared. Then we have a 7x and an 8x, so that would be 15x. And then lastly, we have 7. So that's your multiplication. So we had addition, subtraction, multiplication, and now let's look at division. So this is going to be written usually with that slash bar. This is f divided by g of x. It simply means we're taking the f of x function and we're dividing it by the g of x function. And now we're going to write it a little differently, because with division, we have a numerator and we have a denominator. So the numerator is f of x, which is x squared plus 8x plus 7, and the denominator is g of x, which is x plus 1. Now, sometimes that's as far as you can go, and you have to stop there. But in this case, we can see that the numerator factors into x plus 7, x plus 1, and now that factor in the numerator of x plus 1 will cancel with a factor of the denominator, or rather the entire denominator, x plus 1, so that the resulting quotient is x plus 7. X plus 7 is the final answer. So that's question number 1 from homework 21A. Okay, so for number 2, it's going to be very similar, except that instead of using only variables, we are going to be evaluating as well. So in my version of question number 2, this is the f of x and the g of x that are given. And for the first part of the problem, we have f plus g of negative 1. And f plus g of negative 1 simply means that I am going to take f of negative 1 and add g of negative 1. And so now I need to figure out what f of negative 1 is and g of negative 1. So these parentheses are just so you can see I'm replacing f of negative 1 and g of negative 1. So here's my f function. If I plug in negative 1 to here, I end up with negative 1 squared minus 16, right? That's f of negative 1. G of negative 1, I plug negative 1 right here, and I get negative 1 minus 4. So what is that? That's 1 minus 16, which is a negative 15. And then negative 1 minus 4 is a negative 5. So that this ends up simplifying to negative 20. So that's f plus g of negative 1. The next question is f minus g, not of negative 1. Now they've changed the value to 4. So I have f of 4, g of 4, and instead of addition, we have subtraction. So I am turning all of these additions into subtractions here. And I am turning all the negative 1s into 4s. So here I have 4 squared minus 16 over here. This would be 4 minus 4. So this is 16 minus 16, which becomes 0. 4 minus 4 is also 0. So this is 0 minus 0, which is 0. So I don't know what your answer will be for part B, for the second part. It could end up being 0. It could end up being something else. This just happens to be the number that was put in here. So the next question then goes to multiplication. And instead of a negative 1 or a 4, we're looking at f times g of negative 2. So first of all, I'm turning subtraction into multiplication. And then I am turning all of the 4s now into negative 2s. Okay, so f of negative 2 times g of negative 2. I plug in negative 2 to the f function. I plug in negative 2 to the g function. This is going to give me 4 minus 16, that's negative 12. Negative 2 minus 4 is negative 6. Negative 12 times negative 6 is a positive 72. So that's f times g. And lastly, we have f divided by g. So now I turn all of the multiplication symbols into division symbols. Divided by, divided by, divided by. And instead of negative 2, it's going to be f divided by g of 3. So I'm changing all of these values to 3. F divided by g of 3 is f of 3 divided by g of 3. Plug in 3 to the functions. F of 3 is 3 squared minus 16. So 3 squared minus 16 is 9 minus 16, which is negative 7. 3 minus 4 is a negative 1. Negative 7 divided by negative 1 is positive 7. So that is question number 2. Okay, we've finished algebra of functions, and now we move on to composition of functions. Composition of functions is on the final exam. It's part of the extended response, and it is worth 2% of the final exam. So still not a huge amount, but this is important. What is function composition, or composition of functions? Well, first of all, function composition has its own notation. So in number 3, it's going to say find, and what is written is this f, which of course stands for the f function. And then there is this little open circle and a g and then x. Okay, so sometimes you see it written like this, and then sometimes you see it written with extra parentheses. And in the case of MyOpenMath, they're going to write it with the extra parentheses. So first of all, let's look at how to pronounce this. We say this is f of g of x. So you're already used to saying that this is g of x. This little extra circle here is going to then be read as of, f of g of x. And this little circle, and I'd recommend you look in the textbook or look at MyOpenMath so you can see the notation. It's smaller than an O, okay, so this does not read fog. It's smaller than an O, but it's larger than the little degree circle, and it's hovering midway between the two letters. So look at the textbook, look at MyOpenMath, see how they're actually writing it. It's a new symbol we've never used before. And this symbol, this little small O that's hovering in between the two letters, is used for function composition. So what is function composition? Function composition is a little bit like those Russian dolls, where you put one doll inside another doll inside another doll. What we're going to do is we're going to nest one function inside of another function. And in higher math, you might see one function nested inside another function, nested inside another function, inside of another function. For this level of math, we're only going to see one function stuck inside of one other function. So let's see what happens. Notationally, this is identical to this. They both mean the same thing. And this is also read f of g of x. So what we're going to do, and let me color code this. Let me rewrite g of x in blue. I'm going to take this f of x, and I'm going to still copy f again. I'm going to replace g of x with what g of x is equal to. G of x is 9x minus 2. Okay, so here we go. 9x minus 2. And so what I'm going to do here is I'm going to plug in not a single value, not just f of 3 or f of 2, not a single value into f, but an entire binomial. This entire binomial is going to get plugged into the f function. So the f function is 7x minus 3. So normally if you want to plug in a number, you just do 7 times that number minus 3. But instead of plugging in a single number, I'm plugging in 9x minus 2. So 9x minus 2 replaces the x in 7x minus 3. So now, to simplify this, you just use the distributive property and combine like terms. 7 times 9x is, of course, 63x. Then you have 7 times negative 2, which is negative 14, minus 3, which is negative 17. So 7 times negative 2, negative 14, minus 3 is negative 17. So that's question number 3. So now to prepare you to do self-check 3 in the homework, which is from 9.1, I want to walk through example 3 that's on page 756. And example 3 gives you two functions. You have f of x is equal to 2x plus 1, and g of x is equal to x minus 4. And for part A, we need to find f of g of 9. So what is f of g of 9? Well, it's the same thing as f of g of 9. These both mean the same thing, written in two different notations. So what I want to do is I want to figure out what g of 9 is. So g of 9, if you plug 9 into the g function, you get 9 minus 4, which is 5. G of 9 is simply 5. So now I am left with f of 5. So now I plug the 5 into this function over here, and 2 times 5 plus 1 is 11. So that's part A. For part B, we need to find f of g of x. So in this particular case, we were looking for a particular value. We were evaluating the function composition at a single value. Here we're doing what we did in MyOpenMath problem number 3, and that was we are going to be finding f of g of x. So here's f of x, and inside of f of x, I'm going to plug in the function g of x. And the order does matter. If the g comes second, you need to put it inside the f, okay? F of g of x is not the same thing as g of f of x. So if the order is backwards here, then this order would also be backwards. So now when you plug in g of x to the f function, g of x is x minus 4. So for the f function is 2x plus 1. So I'm going to write 2 times parentheses plus 1. And I'm replacing the x of 2x plus 1 with the entire expression x minus 4. And so now I end up with 2x minus 8 plus 1. So that gives me the final answer of 2x minus 7, right? Because minus 8 plus 1 is minus 7. Okay, so that's part A and part B. And then for part C, I'll do part C up here. I'm doing another evaluation at a specific value. Instead of f of g of a value, this time it's going to be g of f of negative 2. So what is g of f of negative 2? That's going to be the same thing as g of f of negative 2. So let's figure out what is f of negative 2? If you plug in negative 2 here, you get 2 times negative 2 plus 1, and that's negative 4 plus 1, which would be negative 3. So now we just need to plug in negative 3 into the g function. Negative 3 minus 4 is negative 7. Okay, so that should prepare you then for self-check 3, and that will also give you the practice that you need for the fourth question on MyOpenMath, which has a video, so if you need further explanation, you can watch that video. So that covers all of 9.1, and next we're going to look at 9.2. Okay, so we want to continue being prepared here for homework 21A, and the second half of 21A, questions actually 5 through 10, are going to come from 9.2, inverse functions. The first thing we want to talk about is a type of function called 1-to-1 functions. And I can show this to you through a mapping diagram. So let's say I have some values in the domain and some values in the range. Let's say my values are negative 1, 2, and 5. And let's say the values in the range are 3, 7, and 10. If I have a function that takes each of these values of the domain to a distinct value of the range, that is a 1-to-1 function. The key idea of a 1-to-1 function is each element of the domain maps to a unique element of the range. So none of these domain elements are going to be mapped to the same range element. And with a 1-to-1 function, you can actually go back the other way. You can trace where each of these came from by just going back the other way. So a 1-to-1 function is an important thing because it's like a reversible process, okay? So putting on my sock and then taking off my sock is a reversible process. When I burn my sock, that's not a reversible process. A 1-to-1 function allows you to go back to where you came from. Now, a simple way graphically to tell whether or not you have a 1-to-1 function is the horizontal line test. Back at the beginning of the semester, we talked about the vertical line test. The vertical line test was used to determine whether or not you have a function in the first place. So we do still want to see, let's just quickly review that, okay? So let's say you have a graph. Okay. If you can draw a horizontal line through every single part of this graph and never hit the graph more than once, then the graph passes the vertical line test, and that means you do in fact have a function. So this one passes the vertical line test, so this one is a function. Now compare that to this graph. This graph, which is a circle here, if you draw a vertical line, you can see that the vertical line will intersect in more than one spot, and so this one is not a function. So a vertical line test is used to determine whether or not you have a function. Then there is the horizontal line test, and the horizontal line test is used to determine whether or not you have a 1-to-1 function. Of course, if your graph is not a function, it can't be a 1-to-1 function either. So this is neither a function nor a 1-to-1 function. Going back to that previous example, this one not only passes the vertical line test, but for the horizontal line test, every single possible horizontal line I draw, each of these horizontal lines also do not intersect more than once. So this one passes the horizontal line test, And since it passes the horizontal line test, that means you do have a one-to-one function. Compare this graph to the parabola. So is this quadratic a function? Yes. It will pass the vertical line test, no problem. We do have a function. We know that parabolas, quadratic functions, are parabolas. Those are functions. But this graph fails the horizontal line test, which means that it is not a one-to-one function. And you can even see that algebraically. If this is the function f of x is equal to x squared, if you were to make a mapping diagram, obviously there's an infinite number of elements in the domain because this is going to go through an infinite number of numbers, but let's look at just two of them quickly. -2 and +2. When you plug in -2 and when you plug in +2, in both cases, since -2 and +2 are both 4, we would say that -2 maps onto 4 and +2 maps onto 4, and that's fine as a function, but that's not a one-to-one function. I have two elements mapping onto the same range element, so that's not a one-to-one function. So when you do questions 5, 6, 7, and 8 of MyOpenMath, you just need to determine whether the graph is a one-to-one function. First of all, determine whether it's a function in the first place by seeing if it passes the vertical line test, and then you can check to see if it passes the horizontal line test. And anytime it passes the horizontal line test, anytime it intersects at most one time, then it passes, and therefore it is a therefore it is a one-to-one function. So that's the graph part of a function. So now, what is the significance of a one-to-one function? In order for a function to have an inverse, it has to be one-to-one. So the inverse is the reverse process. If I want to reverse and go back the other way here, I can't, because I don't know if I start at 4, if I should go back to -2 or +2. But if I have a different type of function, and that function maps each of these only once to distinct elements of the range, then I could actually go back the other way, such as in the case of the previous mapping diagram I showed you. Now, algebraically, what we want to know is how do we find the inverse of a function algebraically? We need a rule that is going to send everything home. Okay, let's start with really something simple and intuitive. If I have a function that doubles numbers, okay? So I take a number and I double it. How do I go back to where I was? I half the number, right? So if I double 3 and I end up at 6, and I want to send 6 back to where it came from, I simply divide by 2. So it's the reverse process. It's kind of like when you're driving, if you take a right and then a right and then a left, to go back home, you would take a right and then a left and then a left, right? You just reversed the process of getting to that location. Now the inverse function has its own special notation. So we said the inverse function of doubling would be to half the numbers. The inverse function notation, this is the inverse function notation. Inverse function. We have this -1, and it's in between the f and the x. You just say this as f inverse of x. F inverse of x. It's important to note that this little -1 is not an exponent that sends f of x down to the denominator, okay? It's just a special notation that's used for the inverse function. So when you see this, f inverse of x is not equal to 1 over f of x. All right, that's not true. This is just the notation for the inverse function. Okay, so now we want a step-by-step process for finding the inverse. And here's the step-by-step process, okay? So, step-by-step process for finding the inverse. Okay, step number 1 is you're going to replace f of x with y. Step number 2, switch x and y. Step number 3, solve for y. And step number 4, replace y with f inverse of x. Okay, so we want to see all of these steps being used in a problem. So let's look at question 9 from MyOpenMath. So question number 9 from MyOpenMath, for the version that I have, it came up as f of x is equal to 12x plus 9, and it asks that you find the inverse. You want to find f inverse of x, okay? So let's go through these steps. Step number 1, you replace f of x with y. So I'm going to rewrite the original function, replacing f of x with y. Pretty easy. We already think of f of x and y being interchangeable. Step number 2, switch your x and your y. So every occurrence of x gets replaced with, every occurrence of y gets replaced with x, and every occurrence of x gets replaced with y. So we're switching the x and the y. That's step number 1. Here's step number 2. Step number 3 is to solve for y. So that would mean that I need to subtract 9 from both sides. So I subtract 9 from both sides. And then I need to divide both sides by 12. So y is equal to x minus 9 divided by 12. Okay? So that was getting y all by itself, and that is step number 3. And then step number 4 is simply to rewrite this, replace y with f inverse of x. So here you just replace y with f inverse of x, x minus 9 divided by 12. There you go. There's step number 4. So it's a pretty simple process. Just follow the steps. Replace f of x with y. Then you switch your x and your y. So every occurrence of y gets written as x. Every occurrence of x gets written as y. Then you go through the algebra of getting y all by itself. You solve for y. So we subtracted 9 from both sides. Then we divide both sides by 12. And then once you get y by itself, you simply replace that y with the f inverse of x notation. And what this means is that this function down here is actually the inverse of the original function. Okay, so let me write this up here. F of x equals 12x plus 9. F inverse of x is equal to x minus 9 over 12. Okay. sorry. Now you can see it. Okay, so here's f of x is equal to 12x plus 9, and here's the inverse function that we found. In question number 10, we're going to be looking at two functions that are going to be written like this. And then we're supposed to do a function composition. Okay, so let's say that instead of this being called f inverse of x, let's say that this one was actually called g of x. So let's say the original problem looks like this. Here's question number 10. They're going to give us two functions. They're going to call one of them f, and they'll call the other one g. Now, in reality, we know that g of x is actually the inverse function. But they're just going to give you two functions like this. And then what they're going to do is for part A, they're going to have you find f of g of x. So we're going to plug the g of x function into the f function. So here's the f function. It's 12 times x plus 9, okay? So that is the function for f, 12x plus 9, 12x plus 9. Except instead of plugging in an x, I'm actually plugging in what? G of x. So I'm plugging in g of x into the function. What is g of x? G of x is x minus 9 divided by 12. X minus 9 divided by 12. Okay? So now what happens? 12 here on the outside cancels with the 12 on the inside. And this gives you just x minus 9. And then you still have this plus 9. And that is equal to x. If you have your foot, and then you put your sock on, and then you take your sock off, you end up back with your foot. That's an inverse function for you. So the reason that f of g of x ended up simplifying to x is because, as we already knew, f of x and g of x are inverse functions. So let's look at this the other way around. In part B, we need to find g of f of x. So part B is to find g of f of x. Sorry, I erased this. This was your g of x right here. Okay, so g of f of x means I'm going to take the g function. What's the g function? The g function is x minus 9. So x minus 9 divided by 12. And I'm plugging in, instead of plugging in x, though, I'm plugging in f of x. Well, what is f of x? F of x is 12x plus 9. So if you have a 12x plus 9 minus 9, that is just 12x, and the denominator is 12, and that simplifies to x. So it is not usually the case that f of x is equal to g of x, okay? So in general, f of g of x is not equal to g of f of x. This is what I meant to say. In general, f of g of x is not equal to g of f of x. In this case, however, they were equal. They were both equal to x. But when f of g of x is equal to x and g of f of x are equal to x, they're obviously equal to each other. What we have, if they're both equal to x, then that means that f of x and g of x are inverse functions. That's the test. How do you know if two functions are inverse functions? If you plug one into the other, and you end up with x. If you do function composition on them and you end up with x back, that's how you know you have inverse functions. So for part C of question number 10, the answer is inverse. So g of x is called an inverse function of f of x. Right, so that wraps up homework 21, part A, and that would also prepare you for 9.2 and 9.2. You need to find algebraically. The one thing I didn't go over, but this is something you should already know how to do, is how to graph lines. Now, in this particular case, so in self-check 5, you have a function, and then you have to find its inverse function, and you have to graph both of them. They are both linear equations. You already know how to graph linear equations. If you are confused at all, just look at example 5. It will remind you of what it looks like to graph two linear equations. Okay, so the next lecture will cover homework 21B.